An unusual way to start a section, but I want to say this section is really about d electrons. In your textbook, it's entitled Color and Magnetism. You can trace that to partially filled d subshells, and when we observe a color, we see the wavelength of the reflected light. We see the complement. Visible light has the appropriate energy to cause d electron orbital transitions. The electrons go from a lower energy level to a higher energy level. Okay, that's really what this is going to be talking about. Some points to make. If we happen to have a completely filled or completely empty d subshell, the material will be colorless. It will also be diamagnetic. What's going to happen in section 23.6, we're going to talk about orbital splitting, and we're going to say how it depends on the ligands and how these ligands are arranged in something called the spectrochemical series. You've already seen a little bit of this with possibly not realizing it. Remember back in chapter 17, we had a copper 2 plus aqueous solution. We put in some ammonia, and we made a copper complex. Well, this copper really had 6 waters around it, 6 ligands. When we made the complex, that water, the 6 water ligands, they were replaced by 4 ammonia ligands. So that's the one you've seen before. If we were in class, I would have a demo with nickel, where we would start with a green nickel 2 plus solution, where this is the ligand, water. And as we would add different reagents, what would happen is we would see a color change. When we would put in an amine ligand, we would see it turn blue. Okay, so that's what we observe. So let's talk a moment about color. If we were in the classroom, I would point to someone and say, they're wearing their red OSU shirt. And then I would say, that means the dye in their shirt is absorbing green, which is 490 to 560 nanometers. Then I would say E is equal to H nu, or Hc over wavelength. So if we know the wavelength, we can calculate the energy of the transition. Okay, that's what we would have done in class. We're not in class. Many types of experiments use spectrochemical analysis, and what they do is they have a sample and they look at the spectrum that is displayed. So I noticed your new edition has a different color, but I'll stick with my old color. This is sort of a pink color. Pink is kind of red. If I look at where we are absorbing light, we are absorbing in the green. If I go back to the color spectrum, I hate to draw on it, but I will, what happens is we see the complement color. So that's where the color comes in. Now let's talk about the d electrons. Back in chemistry 1210, you learned that there were 5 different orbitals that are labeled d, and there they sit. And so now we're going to try to explain what's happening in a complex. People in valence bond theory said, it is going to depend upon a covalent bond, and it'll either be called an outer orbital or an inner orbital. Just like Bohr, theories get refined, but I like to use this one in class because I want to bring d orbitals back to the front. So if I have an iron atom, that is its electron configuration. If I make an iron plus 3 ion, I am going to remove the electrons from the outermost shell. And from 6, we are now going to have 5 electrons. This is going to be a D5. So when people were working in the lab, what they found when the ligand was water, they saw there were 5 unpaired electrons. When the ligand was cyano, they found there was only 1 unpaired electrons. Remember, this is an early theory, and I want to present it before the next section so you really get into the swing of it. They called the first one with water an outer, and they named it sp3d2. They called the second one inner, and they named it d2sp3. As we go back, the complex that had, on the next slide, I've tried to explain it. Here is our electron configuration for iron, where I've drawn the 3d and the 4s2. When I make the ion, what I have done is I've removed the 4s electrons. I removed one of the d electrons. So I have 5 unpaired electrons. So now let's try to explain the observations using valence bond theory. When we have the complex that is entitled sp3d2, what has happened? Well, that is called the outer orbital complex because what we do is we draw out everything in that next n level. You see there's a 4s, a 4p, and a 4d. Let's say we have 6 ligands coming in and we have 6 electron pairs. That's what these little X's are. 1, 2, 3, 4, 5, 6. The electron pairs have moved into those orbitals, and we can account for our 5 unpaired electrons. So they call this an S because there's the S. They call this a 3p because there's the 3p. They call this a D2 because there are the 2 Ds. And it worked for water in it because it had 5 unpaired electrons. Then, when they did the cyano complex, they came up with a different explanation. And I don't think you're going to like it either because look what they've done. They have made the Fe3 plus ion look like this. Now, we know that is simply not allowed. That's why this theory did not stand. They still drew out all those orbitals out here. And when they brought the 6 ligands in with their 6 pairs of electrons, 1, 2, 3, 4, 5, 6, they were able to account for the observation of 1 unpaired electron. Now, this is not the proper or the current one people are doing, but to me, it helps you remember how do the d orbitals function. That's really why I have it here. Complex. On my last slide, I say, well, it looked to some that you could explain structural and you definitely could explain magnetic properties, but it did not tell you anything about the color. How are you going to explain that? So here is a picture coming out of section 23.6. It is called crystal field theory. Draw your eye first to place I've just marked. What you see are 5 degenerate d orbitals, and they are labeled free metal ion, no crystal field. When I put them into a crystal field, that raises them in energy, they remain degenerate. When I put them into what is called an octahedral crystal field, I see splitting of these orbitals. I see 3 go down, they're labeled the T2G. I see 2 go up, they are labeled the EG, and I will say that delta OCT is equal to E is equal to h nu, E is equal to hc over wavelength. Now I have a way to talk about color, think back to the color wheel, by considering what is the splitting between those 2 energy levels. More in the next section.